think that now we can start our first session in the spring semester of this 25 year. This is a 29th season of our seminar, and it is my pleasure to announce a talk of Georgii Riabov with the stochastic flows of kernels. This is a continuation of the talk which was delivered last semester. Please, Georgii.
Okay, thank you for introduction, and I'm sorry for the mess with the links. So this is the second and hopefully the final part of the talk about the general theory of stochastic flows of kernels. I will briefly recall the framework, the problem that I was working on, and what I presented last time. So I consider a locally compact separable metric space M. By PM, I denote the space of probability measures on M. A kernel on M is a measurable mapping that sends each point of M to some distribution of, on M. By E, I denote the space of all kernels on M equipped with a cylindrical sigma field. Having two kernels K1 and K2, we as usually define the composition K2, K1 in the following way. So we first apply K1, then K2. Okay, and the main issue that I was facing with is that the composition of kernels is a non-measurable operation. Okay, so if we consider E with a cylindrical sigma field, then such operation is not measurable, and this causes some problems with actually with the definition of composition of random kernels. To solve this issue, Lejean and Raymond introduced a notion of regular distribution. So nu is a regular distribution on the space of kernels if one can find a measurable mapping P. Okay, so this is a mapping of the space M and the space of kernels E into the space of measures on M, such that for each x, pk of x almost surely coincides with k of x. Well, yeah, so in some sense it is a measurable modification of like an identity mapping on E. And by a stochastic flow of kernels on M, the definition was given by Lejean and Raymond. We understand the family of random kernels on M such that the distributions of kernels KST stationary, so depend only on T minus S and are regular, then the evolutionary property holds in the following form. So the composition of KRS with a measurable presentation of KST at point X coincides with KRT almost surely. And here the the exceptional set can depend on X, R, S, and T. Next, we have a property of independent increments. Okay, so on disjoint intervals, kernels act independently. And properties 4 and 5 are analogs of a Feller property for transition functions. Yeah, so here f is a continuous function that vanishes at infinity. And the property 4 means that uniformly in probability, the action of k0t to f converges to f. And property 5 means that in probability, the action of k0tf is continuous in x and also vanishes at infinity. We can think of stochastic flows of kernels as of models of motion of particles in a random media in which, in some sense, particles can turn into clouds. Well, it means that KST of x describes the random distribution of positions of a particle at time t that was located at x at time s. Such situation occurs when we deal, for example, with the solutions to stochastic differential equations without strong uniqueness. And last time we discussed one of the simplest examples of such kind, the Tanaka SD. So this is the SD. dxt equals to sine xt dbt. B is a Brownian motion. And okay, if we have a solution to such equation, then we can apply the Itov formula to f of x of t and get f of x plus the integral from s to t f prime xu sine of xu dbu, okay, plus 1/2 the integral of f double prime of x of u du. And this equation can be extended to kernels in the form that you see on the slide. And it turns out that this equation has solutions of flows of kernels that are not the flows of mappings. And actually all kernel solutions were characterized by Lejean and Raymond. Actually, they are characterized by the distribution of a probability that when hitting 0, solution goes up.
But when we characterize all solution, we have to take some additional additional noise, like Bernoulli sequence, which
Yes.
give us probability for
Yes, so the noise of K is strictly bigger than the noise of B.
Okay.
And as another example that that is not related to equations, we can actually look at non-random kernel K, which is just convolution with a Gaussian density with mean x and variance t minus s. And such stochastic flow of kernels corresponds to the motion of independent Brownian motions that start from every point of the real line at all the times. Yeah, and let me give the following definition. So the endpoint motion of a stochastic flow K is the following function, P and T. So here X is a point of it's endpoints of the space, and P and T is the probability that on average under the action of this flow, the point X will be in set B.
Georgi, I have a question relative to the example 2. In which sense it corresponds to the motion of independent Brownian motions?
Exactly in the sense of endpoint motions, because now if you put here this definition of K, you will get that P and T X P and T X, let's say B1 times Bn will be equal to the product, okay, let's say a probability that X belongs to Bi.
So in the sentence which you describe example 2, you mean that from every point we have a lot of Brownian motion starting, yeah?
No, we have like one Brownian motion, but when they meet, so there is no interaction between them.
Yes, but
yes, they all like move independently and start from all space.
But you see, suppose that you take xi in those in the line when endpoint.
Yeah, exactly. So when xi are equal, then you have like two motions that are in one point, but when they move like independently.
Yes, yes. So, but not only two. Yeah.
any number. Yes.
Yes, exactly. This was my point. So this is the reason why we call it kernel. Okay.
Yeah. Okay. So if we define if we define like the transition functions for endpoint motions in such a way, then in fact we get a failure transition functions. And this is a consequence of properties 4 and 5 of this definition. And actually 2 is also important. Also, such transition functions are consistent in the sense that the transition functions Pn define all transition functions Pk when k is less than n. And well, famous result by Lejean and Raymond that conversely, when we have a sequence of failure transition functions that is consistent, then one can construct a stochastic flow for which these functions define endpoint motions. Okay, so my aim was to initially it was to work with this measurable presentation function, which does not look naturally. And what I was able to do is the following theorem. So we start with the consistent family of failure transition functions. Then there exists a stochastic flow, K, for which Pn defines endpoint motions. The distributions of all kernels from the flow, actually, they have one measurable presentation. And moreover, it can be chosen such that, okay, so P composition P is equal to P. Then also, without exceptions, a kernel KST coincides with its measurable presentation. So instead of KRS, P, K, ST, we can simply write KRS, KST, and this will be equal to KRT. Okay, so it depends on X here, and the equality is almost sure. And also, it was possible to construct the flow in a measurable way with respect to all arguments st and omega. Okay, so my aim is to actually discuss the proof of the theorem, and before that, I will briefly recap what was done last time. On my previous talk from the sequence Pn, we constructed a Feller convolution semigroup. Here, nu T is the distribution of K 0T. Okay, so we constructed this, actually it is a semi-group of distributions. And we found a common measurable presentation. And I also need to recall some steps of the construction. Okay, so by pi n t of x, I will denote a probability measure. So this is a distribution of n probability measures, which which has the sense of the joint distribution of values of the kernel at points x1 to xn. It is characterized by this equality, and also this is a consequence actually of this Feller kind property that these measures are continuous in T and X, and also by definition the measure P2 when we start, so the two-dimensional distribution, when we start from the same points, it is concentrated on the diagonal.
What does it mean, concentration on diagonal for this PT2? Because it is defined on measures, yeah?
Yes, yes. So look at pairs of measures.
Yes.
Of the form mu mu.
I see. So it means diagonal is space of measures.
Yes.
Yeah?
Yes. Okay. This is equal to 1.
Okay.
So next, what we did, we looked at a countable dense set and defined by PT a probability measure on the space of sequences of measures. So in the sense that actually PT pi t is the joint, pi t will be the joint distribution of the values of the kernel case 0t at points Zn. And then we recover the distribution of kt by following approximation procedures. So we can write M as a union of compacts that are increasing. Lk is a compact that is contained in the interior of Lk plus 1. zeta k is a truncation function that is equal to 1 on Lk and whose support is contained in Lk plus 1. And from the fact that pi2 is concentrated on the diagonal, we can prove that there exists a sequence epsilon j that decreases to 0, and such that, okay, if time t is less than j, if xy belongs to Lj, and the distance between x and y are less than epsilon j, then the probability that measures will be at a distance at least 2 to the power minus j will be less than 2 to the power minus j.
Mhm.
Okay, and then we defined an approximation in the following way. So mxj is the first element of the dense set that is at distance epsilon j over 2 from x. Then from this approximating sequence, we construct a sequence of measures in this way. And choose a partial limit of this sequence. It was proved that there exists a possibility to choose a partial limit in a measurable way. So in this sense, when we have a sequence of measures, which we put at points like k z1 is equal to mu1, k z2 is equal to mu2, and so on, then for every point x, we can choose a subsequence of indices, and from the corresponding measures, we choose a limit point. So I mu of x is actually a distribution of k at point x. And then we define the measure nu t as the image of pi t under the mapping I. Then by E small, we denote distribution from the space of kernels to the space of sequences of measures that for each kernel k returns its values at this dense set Z. And it is not hard to see that the composition of E and I is the identity mapping. I mean, if you place measures mu at point Zn, then apply I and then evaluate them at points Zn, you will get the same sequence mu. And from this, we deduced that the composition of E and I is actually a measurable presentation of all measures nu t. And these measures are actually the convolution semigroup that we were looking for. Okay, so having said all that, I will turn to the construction of the flow. So at first, we need to define a probability space. Okay, so by Sn, I denote the probability space of the following form. So this is the space of sequences of measures with the probability pi 2 to the power minus n to the power z. Intuitively, for every point of this space, so this point is a countable collection of sequences of measures. For each sequence, we can construct a kernel, and actually the kernel I omega NL will be the random kernel from the flow that I will construct. Okay, but we also need this evolutionary property, and to get this, we can consider a mapping from Sn to Sn minus 1 in the following way. So it takes like a sequence of kernels of order 2 to the power minus n, and transform it into the sequence of kernels of order 2 to the power n minus 1 in such a way that will like impose the evolutionary property. Okay, so these mappings are measurable and surjective. Well, here I write why they're surjective. Actually, you only need to look at the sequence of measures mu0 that are concentrated at points of this dense set. And this sequence has a property that actually the mapping I moves this sequence into the identity kernel. Yeah, because when we evaluate this measure, then we have a sequence that converges to x. Yes, and then delta measures at this sequence, they will converge to delta x. So our mapping will pick exactly delta x. And well, from this actually it follows that this identity kernel is invariant under our mapping P. Okay, so then if we consider the element of the space Sn minus 1 and define omega n as mu0 at even points and mu n minus 1 at odd points, then this will cancel, and I composition E, we know that this is an identity mapping. So we have a surjective mappings pi, and the probability measure Pn under this mapping pi turns into Pn minus 1. This is a consequence of the semigroup property of nu. Okay, so in this framework, it is known that we can look at the inverse limit of these probability spaces. So it's a sequences omega, so omega n belongs to Sn, and such that omega n is sent to omega n minus 1 by pi. And on this probability space, there is this probability measure such that the distribution of omega n is actually Pn. And here the main achievement is that on such space it is easy to construct random kernels K such that we have already the evolutionary property, like without exceptions, when S is a dyadic of order 1 over 2 to the power n. Okay, and we like we do like 2 steps like to S plus 1 over 2 to the power n. Also, on this space, we can define the filtration for dyadic S and T. AST is the sigma field generated by pings omega and u, such that u over 2 to the power n is from S to T. Okay, for disjoint segments and S, RS and ST, these segments are independent, and this is indeed a filtration. Okay, and now we can define a family of random kernels. So this is a kernels KST. D means the dyadic. Okay, when S and T are of the same order, then we define KST as the composition of kernels like on that act on one step, yes, of the same order. If ST are any the dyadic numbers, then we define dk as a measurable presentation of dkn. Well, and we also need to define what is k with indices t and t, and we define it as the identity kernel. Then, with such definition, we have that this family of random kernels is invariant under P. Point 2 describes how it works like for one step. And again, from the semigroup property of distributions of distributions nu, we can prove that the distribution of dkn st is mu t minus s. And again, since all distributions nu share the same measurable presentation, we can deduce that dkst by a construction on dyadic numbers. We have the evolutionary property like without exceptions. From this, one can prove that so this lemma will be needed for evolutionary property of k, but almost surely. Actually, yeah. So lemma says that for any random element, for any random measure on M that is independent from ST, we have the following equality. Okay, so if S and T are of order 2 to the power minus n, then mknst coincides with mkst, almost surely. Okay, so since this kst is equal to dk sum mst, m is less or equal to n, then it is enough to coincides with mkn plus 1. Yeah, but this is actually a consequence of our construction, because we have a quality like for two steps. Also, we have such equality with measurable representations, which is needed like to integrate over. Yeah, so okay, yeah, if we look at of the measure of x, where equality holds, then by independency and by measurability, we can integrate it over the distribution of m, and this is equal to 1 by construction. So almost surely for almost all x, we have this equality, and then we get this equality. Okay. As a consequence, we have the evolutionary property on dyadic numbers almost surely. Okay, and now the last step is to extend this that is defined for the dyadic moments of time, like to all moments of time. And I proved the following lemma to do this. So if f is a continuous function of two probability measures on the compactification of m, then if we like apply mu to kst and then u to kuv, and then apply f, so this object can be to all values of s, t, u, and v, and all measures mu and nu that belong to some in the set of measures. Okay, so actually it is enough to consider functions that are products of functions like j of mu, h of nu. Here j is the integral of some function a, and h is an integral of some function b. And here a and b, they are functions on m, m to the power n. So first, let's consider the case when A and B have compact supports. So what we need is to find a continuous extension of such function that can be written in the following form. And we can just evaluate the function h for different displacements of okay, so when t is less, and we take first expectation with respect to kuv, yes, and then take the expectation with respect to kst, and get the following expression, which is easy to see that it is continuous in all arguments. Yes, so for example, from S to T, and T is then we use the evolutionary property uh, for for K, which we have. Yes, and get the following expression for the function h. And it is also well, it is not so easy as in the case one, but it is also can be proved that it is continuous in all arguments, which is a consequence of the failure property of Pn. Well, and the last case is analogous to the case two. Okay, so it follows then when A and B have, let's say, have compact supports in M, then we can find indeed a continuous extension of the function we need. In general case, we can multiply A and B by these truncation functions zeta. In this way, we get a sequence of G, J, and Hj, and for each J, we know that there is a continuous extension of the expectation.
Do we need that the measures nu, mu are also concentrated on the sum compact now or not?
No.
No. Yeah.
No.
But you just said that you take the function of that kind due to the possibility to apply Stone-Weierstrass theorem, but you apply Stone-Weierstrass theorem, as I understand, on the compact of measures, or not?
To
Yeah, here
functions.
this is a compact C, yes, and you just take.
No, I didn't consider compact C up to now.
Mhm.
No, just we look at the function f. It is a continuous function on a compact.
Yes, it is continuous function on what? On
Like
P M with tilde. Is it what? Compact, some compact subset. Yes. M with tilde. This one.
M hat is a
Yes.
compactification of M.
Compactification. I see. I see. Okay, and then you claim that it is enough.
No, but you see that I take mu and nu from some compact.
Yes, this was my point. This was my point, that you take mu and nu from some compact subset in space of measures. Yes.
Exactly, but in the first case, actually, I don't need it.
I see, but I am asking because even in very good locally compact spaces, the space of measures is not locally compact. Yeah, with respect to Wasserstein distance.
This is because I'm doing all that actually.
Oh, I see. I see. Okay, let's go further. Okay.
Yeah. So okay, so we can truncate functions a and b. Okay, get this continuous like approximations, and then we need to prove that actually fj approximates f uniformly in all arguments. And for this, I need that mu and nu belong to some compact set. Okay, so we know that if this C is a compact set of measures, then they can be all then they have like a big mass on some compact set of subset of M. And also we know that since these one-dimensional distributions of kernels, they are continuous in T and Z, we can also find a compact L such that this holds. Okay, now let's estimate the difference between what we want, yes, and what we have. So if J is large enough, then Lj contains L. So we have these two estimates. Then, okay, so we're estimating by max norms, and we get this line. Then we have Lyapunov inequality. So finally, we get to this expression, okay, which is actually less than 2ab, 1 minus 1 minus epsilon to the power 3n. So how we get the last line? Okay, so we estimate the expectation. First, we integrate only over C. This is a big compact in M. Then zeta j is greater than 1 on L. And then we pass to, from expectation, we pass to the integral. Okay, and here we have that mu, that measure mu over C is greater than 1 minus epsilon. And on the set of measure greater than 1 minus epsilon, this is also greater than 1 minus epsilon. So we get 1 minus epsilon cube. This proves like the uniform estimate, which shows that, well, the which proves what we wanted. Okay, and now why we need this? From this result, we can prove that for like when we consider times from like minus t to t and consider measures from a compact C, then for small enough delta, as soon as all distances between arguments will be less than delta, the probability that the distance between mu kst and nu kuv will be bigger than epsilon, the probability will be less than epsilon. So here d hat is some distance in the space of measures on compactification. Okay, well, and this is actually not hard to show from the previous result. So assume that it is not true. Okay, then we have some sequences Sn, Tn, Un, Vn, and sequences of measures. Okay, such that distances between them go to 0, but this probability is bigger than epsilon. We may assume that all these sequences converge to some sequence St, St, mu, mu. And now we can look at a closed set of measures, of pairs of measures, such that distances between them is bigger than epsilon, and the following continuous function that like approximates this set in a usual way. So here d2 is a distance in the space of pairs of measures. Okay, now if we take large enough R, then what we have? We know that this function has a continuous extension. Also, the function f from arguments Sn, Tn, and so on, it is bigger than epsilon. Okay, and it has a limit. Okay, so this limit must be bigger than epsilon. On the other hand, we can obtain the same limit by looking at values of f when s is equal to u and t is equal to v. But this value is actually equal to 0 because our choice of r.
Mhm.
Okay, so this is impossible, and this proves the proposition. Okay, now we can finally develop the approximating procedure for the flow. We take like increasing sequences of indices nj such that for all moments of time and all pairs of measures that are concentrated on compact sets Lj, we have the following inequality, which was interesting to me because actually this is the same property that I used when we constructed the convolution semigroups. Okay, now for each t by tj we define its approximation by dyadic numbers. And also, again, we know that there exists a measurable way to choose the limit point of a sequence in a measurable way in the space of measures on a compactification of M. Okay, now we define phi kx, which will be an approximation of which will be the value of the kernel in a flow with a non-dyadic moments of time. Okay, so this is a limit point of a sequence of approximations if it is concentrated on M, and some other measure in otherwise. Okay, so and the final step is to define random kernels as follows. So for S and T, approximate them by Sj and Tj, and take the sequence of dyadic kernels, and then take the limit point. And the last step is to take a measurable presentation of this. Actually, this definition is consistent with the definition for the dyadic case, because if S and T are dyadic numbers, then Sj and Tj are equal to S and T. So this is like this sequence just has a limit. So we obtain this limit, and we recall that kernels for dyadic numbers were invariant under P. Also, okay, when S is equal to T, we get identity kernel. What we obtain is invariant under P because P is idempotent. The obtained mapping K is measurable in all arguments because these are obviously measurable since Sj and Tj can take only a countable number of values. Okay, and also actually we have an almost sure convergence of approximations to the limit k. Well, and we can get it also after integrating with respect to some measure kappa. Yeah, so maybe I will go fast now because I hope the idea is clear. If J is large enough, then all moments of time are from minus J to J. All approximations also are from minus J to J. And we just have this inequality. So we have this inequality for approximations, which means that the limit exists. We get this limit like in space of measures on the compactification, but actually we know what is the distribution of this limit, and we know that it is concentrated on M. Okay, so this is, I think, almost all. So we have independence of increments because for dyadic approximations we also had independence of increments. And well, the most technical part is the evolutionary property. Here the problem is that if we define Mj is an approximation of KRS at x, and M is the value of KRS of x, we know that Mj converges to M, almost surely. But now we have to compose like Mj with K Sj Tj and show that it somehow converged to KRT. And the problem is that we don't have almost sure convergence here, but we can prove convergence in probability. So, and again, we do some considerations with compact sets. So all measures mu j and mu, they are concentrated on some compact set with a probability at least 1 minus alpha. Then for this compact set, we can choose fast enough approximations. Okay, and use the obtained inequalities for these approximations. Okay, so this proves the convergence in probability of such measures from the approximating subsequence to the measure MKST. On the other hand, since we have the evolutionary property for the dyadic numbers, we have this equality, and we know that it almost surely converges to KRT. Okay, so here to say. If needed, I can maybe explain some details, but you can also look at the preprint of my work. And thank you for the attention.
Okay, Georgi, thank you very much for the talk. It was rather technical, but interesting. And maybe somebody have questions or comments, please. I have several questions, and the first one is the following. I understand that actually, after you give the condition that these five conditions, especially concentration on the diagonal, then I think that the fact that you work with measures is not so important. I think that the proof follows the way which you already obtained when you construct stochastic flows, which is strong cycle on some locally compact space.
No, no. And the main reason is that, as you mentioned, the space of measures is not local.
Yes, but you overcame this difficulty using this compacts, and then let me ask you. Maybe some sufficient condition can be written in terms of some integrals with respect to measures, some functions from the measures, like entropy, some moments, or some other things, in order to simplify these conditions, in order to avoid distance between measures, at least in the conditions of the theorem.
Yeah. Well, when we did the strong flows, then we had some conditions, but again, so we get flows of mappings, but not of measures.
I'm asking about the formulation of condition on measures in terms of integral, which from some functions with respect to measures.
Yeah, maybe when we can control like some concentration of these measures.
Yes, exactly. It will be not general case, but it will be much more easy to check.
But we proved everything in.
Yes, but imagine you work with a stochastic differential equation, then sometimes
you just need a failure property.
Yes, exactly. And it can be guaranteed in terms of integrals from some functions.
Yes.
Yeah. Also there is the work of D'Aprato related to the following thing. He considered the stochastic differential equation with two white noises which are independent. Then he considered the conditional distributions of the solution when just one of these white noises is given. And he get exactly kernels. Yeah.
In many
Yes, but there are some exams where these flows of kernels arise naturally, and I think it will be good to check that your conditions are satisfied in this case, and that you can get a good flow of kernels in this case.
Yeah, I'm sure that in his situation.
Okay, good. Thank you. Thank you again for the interesting talk. And do you know who will be the next speaker? Okay. Hope next week we will have not two different links.
I'm sorry, I messed it up.
Okay. So hope next week everything will be okay with links, and see you next week. Bye.
Okay, bye.
Thank you.
Thank you.